Everyone, I'm going to present you today in the morning a bit of results from a study we did for the German Ministry of Economics and Energy during the last 2 years, which mainly deal with, is there some kind of way of skipping my presentation? So I'll just keep going. I'm going to present you the key results. Normally we have to talk about this study for like 3 hours, which is more detail, of course, but for you I skipped some regulatory issues which are probably out of scope for Denmark anyway, and I'll just tell you the main results we had from certain technologies we analyzed actually within the scope of this presentation. So usually at Germany it's always we need another study. So we started out and we kicked off to do this study in 2010. So that was like where all German municipal utilities and the large TSOs and DSOs and the regulator and the ministry actually agreed that they need something like a study on how to cope with the higher penetration of DER in the distribution grid, and then it took some time, and we already had a kickoff for the study, and then it was postponed at the day of the kickoff because the a German company dealing with ICT in telecommunications, it might have been the German Telecom, just skipped and didn't want to do the project. So it took some time, and after, well, a lot of issues, we were really like, come on, we just want to do it, and we are more or less creating the Tower of Babel, putting stuff on top again and again and again, and creating stuff which might break sometime. But after a lot of discussions, we finally got to do this study, and what I'm going to present you in 5 more or less short blocks, and normally I plan for some discussion afterwards, but well, it depends on the time and how much I'm going to talk, and how fast, of course. I'm just telling you the key facts in part A. So you all know probably German Energiewende, so it has already been an American word, as I was told last week. We have to cope in terms of grid extension and grid planning with the overall arching aims of putting more renewables into the grid. So we have a strong focus in Germany on the DER feed-in. We already have like 62 gigawatt of renewable fed-in peak load, peak generation, and this usually creates on average like 25% of all electricity we have. It's likely to increase to up to 50% in 2030 and up to 80% envision%, of course, since we never know what's going to happen between now and 2050. We did the study alongside 2 partners, so OFFIS, the Oldenburger Forschungs- und Entwicklungsinstitut für Informatik, Werkzeuge und Systeme, so this is why we abbreviate that. We did that along the WTH Aachen with Professor Moser as a chair, and eBridge Consulting, which are more or less responsible for the regulatory issues in terms of our study. So finally, after some time and hope and prayers, we were given this study. The focus was actually different than the studies you probably know from German DENA, because we also had in mind that we wanted to use new technologies and new control strategies and incorporate them already at planning time for the distribution grid. So our focus was, how can we take ICT and more intelligent stuff from operations time also into account at planning time of the grid, in order just to lower the investment cost we actually have on the grid. So main focus, how to develop our German grids with having ICT and conventional ways as a comparison in mind. So we also had to look for 2030 and 2050 in terms of how the business as usual extension of the German grid would be if we still aim for the DER goals we had in mind in terms of the regulator and in terms of the politics. Also, we had to do a cost-benefit analysis of all the intelligence stuff and all the ICT part we had, and we were also given the right that we might address regulatory issues and problems which might arise if our solution should be put into practice, but is not fitting the conventional ways of regulation. So this is a part I'm going to talk a bit less about. If someone's interested in how ICT for smart grids impacts German regulation, then we can talk afterwards. So I'm here full day. That might be something which is not that interesting in terms of the technical analysis. So main issues we have to do. If there's something red, then it's always about ICT. So because we're from a research institute in computer science, I'll always highlight the parts you can ask more about later in the discussion. So how much grid extension or extension planning is actually needed when you take conventional measures into account? So how is it distributed? Is there a density function where you have more type of grids which shall be extended because they're either in a particular region or they have a particular structure already in place? We also had to deal with which planning strategies shall be applied when you use ICT-based or more like ICT-related smart grid technologies. How can you lower the integration cost of this new technology with the existing legacy infrastructure? Also, which ICT technology shall be used to change the conventional planning? This is what I already mentioned. Which impacts are induced on the security of supply, and of course by more ICT interfaces, because politics in German always say if you introduce more ICT, everyone knows it's going to be more vulnerable. Of course, that's not always true, but people think this way. So if generally the complexity of course rises as you've got more systems. If you've need more backup systems, if you have more interfaces, there's more room for errors to actually occur. But still, you might take risk management and different variations of technologies into account to deal with this very issue. And the fourth question was actually how must the regulation change in the light of the measures we propose within the study. So I'm going now to talk to you a bit about the assumptions we had to make, because as Tom Cruise did on the second slide, we cannot hang from the ceiling and just change the complete grid. We had to do some assumptions not to do something which is really impossible. One assumption we have is 90% of all distributed energy are in the so-called distribution grid, in German Verteilnetz. So for a distribution grid, we took this gray-blue shaded stuff, and I put in like some figures we have around for Germany, so because that might be interesting for you. So we start off with the connection to the UCTE grid, and we have a lot of, of course, in terms of absolute numbers of offshore wind parks, we have like 15, but they only produce like 0.86 gigawatt of power compared to the conventional large generation plants with 73 gigawatts of power. From high voltage, highest voltage to high voltage, we have like 800 substations we have to deal with. And then there's the interesting part in terms of all the loads and all the distributed energy resources feeding into the grid. So high voltage grids, we have around 100 different grids with 95,000 kilometers. For medium, we have 4,500 grids with 0.5 million kilometers. And for lower voltage, we have 1.1 million kilometers and like 500,000 grids. So that's complicated. And those 500,000 grids and also those 4,500 grids are merely operated by like 880 DSOs. So that's like the figures we have to deal with. In terms of the generation, solar parks at high voltage, there's very little. So we got like 2.3 gigawatts. We got 14 gigawatts power at high voltage level in terms of wind parks. So also it grows on medium voltage level, so you see the figures rising, but the gigawatt power doesn't really rise. So we got like 12,500 wind parks and 15.6 gigawatts of power generation connected to the medium voltage grid. Also 40,000 solar parks, or sometimes it's more like PV panels with some kind of aggregator function, and 10.1 gigawatts of power. And in low voltage, where there's virtually no sensors or RTUs or information about the grid at all, we got like 1.2 million solar PV panels, which feed in 19 gigawatts of power, and we got like 500,000 voltage transformers. So that's perhaps an impressive figure, but well, we had to deal with that, and also in terms of the simulation we had to do, that took some time for the colleagues from Aachen. And so we had to come up with a method, of course. So our method actually was like, we did like 5 steps. In this talk, I can't really dig deep into the parts 2 and 3 and 4, because that's like a lot of simulation stuff and a lot of how to create this model archetype grids in terms of MV and LV we had in mind. So basically, I'm going to talk about part 1 and 5 in this talk. So first step we had to take was actually clustering our German grids. So we had the figures from the previous slides, and then we know that that it's not based on the individual member states in Germany, but it's more like based on some kind of density function, some kind of industrial load, some kind of weather conditions, climate conditions, some kind of HV grid model. So we clustered basically with the colleagues from Aachen for load, DER generation capacity, and the envisioned planning already in place from the German Netzentwicklungsplan, so the grid development plan. The second one was actually those heterogeneous grids had to be modeled somehow in some kind of archetype model grids. So we developed typical MV and LV grids, and for HV we had like a German model we constructed from, honestly it was constructed from Google Maps, and then we asked back to the UCTE for some individual electrotechnical properties. The third way was actually then dealing with the individual scenarios. So if you got like your certain archetype grid, then it's not easy for each model grid to integrate the same number of renewables. So we had to cope with different paths of DER into integration into those grids in terms of the development over time and where it can be connected. And then actually there were simulations. So the colleagues from Aachen, they went to the University of Aachen supercluster and rented them for some month, and they even cheated them into buying more computers for them. And actually then we had like the figures in terms of the conventional grid planning we needed. And then there was the interesting part where we came up with the aggregation of the results and also put in our extra intelligence we had in mind when we wanted to cope better with the DER integration in the distribution grid. So basically, current grids, so the conventional planning is based on the models. We had for load and feed-in and generation of DER classes, we had 10 classes for LV, mainly based on load and PV feed-in. For medium voltage, we had like 8 classes based on the feed-in of wind power plants and PV power plants. Distribution analysis was mainly done in terms of load generation, existing cables, and the length of the radial feeders we had to take into account. And that led like to a clustering of DSO in LV, having this figure, so with all those DSOs here, namely, so you see that it's quite rough in terms of the distribution. You cannot really see a pattern or a heavy cluster. That's also true for medium voltage, where we have like this class taxonomy in place. Honestly, it was like quite a bit tricky to get all the data into place, because we had to deal with a lot of data sources, and usually there were not consistency or checked for inconsistency up front. So we dealt with the German Renewable Energy Registry, which exists for all the existing DER resources and wind parks and so on. We had for the HV grid, we had some public TSO data available. And then we found out, okay, we have to go into consultation process with the individual DSOs and TSOs in Germany. And we made like a questionnaire and really grabbed a lot of data from them and asked them to fill out that in order to make our simulations and our knowledge about the grids we had to model actually a lot better. So that took some time, and it's always, and we had some, they really trusted us which was nice because usually they don't give away that much information about their individual MV and LV grids. So, the main changes to 2032 we envisioned or we saw was like we have a double of DR peak generation. So in Germany, it's always about scenarios. So it's Energiewende scenario 1, it's no nuclear, no charcoal-fired plants, and so on. So we had to cope with existing studies already from DENA or in place from the Ministry of Economics. And then actually we picked some scenarios and we didn't choose one. So our study is also compliant, finding existing ways to cope with all existing studies and all existing scenarios. So we have the Renewable Energy 2014 scenario, where the German government says we want to double the penetration of DER into the grid until 2032. That's an average 4% per year we have to cope with. So there's the Netzentwicklungsplan, the NEP. NEP actually means in German cheating, because then it's always funny if you say that, because it's the TSO scenario, and people always think the TSOs want to cheat on them. They have quite the same figures, so they have an additional 5% per year in terms of the DER capacity feeding into the grid. And then there's the stuff in Germany, we call it federalism, which means every member state of Germany may do as it just wants to do. So that's the Bundesländer scenario, and we call it the triplet scenario, because everyone wants to have something from the DER. So we also our member state is also doing a lot of DR. No, we are even doing more DR. No, we have more PVR, but we have wind parks. So everyone wants something, and this is when you have like an additional 3 point. So that's if you go for federalism, then the government it's easy to reach the goal, but that actually means like an additional 10% per year in terms of the DER growth of the existing capacity feeding into the German grid, which is of course a problem from the grid-wise perspective. So we have regional differences. I cannot dig deep into all those individual figures, but actually what you have to say in terms of the results, 75% of all 888 German DSOs face changes. Only 5% of them really have massive impact on their grid, but they are then just really massively impacted, which means actually like they have to extend their existing grid of up to 80% in the next 10 years, which is awkward. And we have some clusters, of course, for the distribution in the scenario. So, of course, having offshore wind parks, and if you're dealing with where does actually the wind blow, so it might be the coast, you have more extension in the north, whereas we always have in the south of Germany or in the western part the individual high industrial loads. There are some differences between the scenarios. So, for example, in the Bundesländer scenario, in the federalism scenario, we have more growth in the west because North Rhine-Westphalia in Germany says we got a different DER strategy and renewable energy strategy, and we have impressive goals to be achieved by our minister president. And well, that differs. So you see that, of course, this is triple the capacity. Some differences on where you have the feed in, but the general story is always the same. So if you just narrow it down to the overall arcing problem, then you see that you can cope with all those scenarios in the pretty same way. Of course, allocation and impact on different voltage levels sometimes differ. So now I come into the original way of business as usual planning for the German distribution grid. So in Germany, we plan for the DER generation peak. And of course, the maximum peak fed in is taken into account, and the lowest annual load in terms of, so the highest load is taken into account, but you then take the lowest limit in terms of the grid extension. So it's probably a situation which never occurs. Because you, if you have like the lowest load, then you may not have the highest feed in, and of course you may not have the highest thermal limits of your lines. So it's like You have some degrees of freedom, but they are all on a certain limit. And we tried, okay, how do we cope with that? So perhaps we can lower some kind of assumptions there. It's really focusing the existing planning state-of-the-art on non-existing use cases. So the reduction by load management is not taken into account for the planning phase. So everyone knows you can do that at runtime, but you do not take that into account at planning time, which is of course a problem if you always plan for the DER peak. And in Germany, when you connect like a small PV panel to the grid, you can choose between people putting you into energy management systems and direct feed-in control or direct generation control. On the other hand, you can say, I don't need ICT technologies, just cut me to 70% of my nominative maximum feed-in capacity in a fixed way. So it sounds a bit weird if you've got like a 10 kV PV panel and you say, oh, come on, if you want to connect it to the grid, it's 7 kV max. But, well, this is how the German regulator envisioned some parts. And we also thought, well, perhaps we might play around with that for the future DER feeding into the grid. Of course, we took all the technical grid-related issues into account, so all the thermal limits and all the voltage regulation and voltage band problems. And then we did like all the simulations. We made the conventional planning, and if there's some violation of the technical issues or technical limits we had, then we said, okay, this scenario way, that doesn't work. We cut this tree in terms of our simulations and start with a different way until it fulfills the technical limits again. So we only had valid technical scenarios in the overall simulation at the very end. So for conventional planning, and those are the figures you have to remember, till 2050 or 2030 on its way, we need a lot of new lines in Germany if we do business as usual. So we need, in terms of the scenarios, between 50,000 to 120,000 kilometers in the low voltage grid, which marks up to 10%. We need like 70,000 to 140,000 in the medium voltage grid. That's an impressive 27%. And 10,000 to 22,000 kilometer in HV level, which is roughly up to 24%. So that means an investment of 23.2 billion euro or 50 billion euro in the Bundesländer scenario, where people do everything they want to do. I think I was looking at the ratio of Danish kronas versus euros, and I think it's times 7 as far as I remember, so that's perhaps an impressive amount of money. 7.5, it's even worse. Okay, so that's anyway, if it's 7.5 or like 7, that doesn't care, so it's too much. So the problem is 2/3 are actually on HV level, and this is 30% of all those investments needed. So if you look at the figures, then you see that okay, this is HV and HV using earth cable. So in Germany, it's always, if you build like a high voltage line, you run into problems because there are people living in Germany, and they got like the strong not in my backyard feeling. They want renewable energies, but pretty much not in their fucking backyard. So no wind power plants and those PV shiny panels, we don't want them, but I want renewable energy and dropping out of nuclear. So that's the NIMBY problem, and that's a big, big problem. So we have to dig deep and always also put the HV cables into earth. And you see that gray shaded stuff, it's more and more and more costly, but that's because it's Germany. Well, so this is too expensive. And also we have a timing issues because 70% of all extensions would be needed within the next 30 years. I just check the time, not to run out of time and to postpone the whole event. So you see that it decreases over the time, but we have a high ramp up, which is a big problem because actually German utilities are not so well off nowadays. And of course we have the grid extension and expansion planning differs over the regions of Germany. So we have the north, west, east, and south, and the low voltage, medium voltage, and high voltage grid. And you see that in the south, due to high PV penetration, we need more or less like the low voltage extensions, whereas at high voltage in the north with the wind power plants, of course, I mean, it's somehow reasonable to do it this way. We need the high voltage and medium voltage extensions. So that's also regional differences we have over, but everyone should pay something like the same grid fee all over Germany, so this is an issue we have to take into account. So you see the big problem, so it's quite costly. We have a lot of stuff to do in the near time, and we really have to make some assumptions to actually deal with this, because otherwise we might run into problems. So change operational way, change the planning way of how to deal with distribution grids in Germany. So this is what we envisioned as intelligent smart grid technologies, but it's more or less for the grid extension cost, we have like this 5 years. So we might cope with some conventional planning stuff, so more number crunching, better grid documented quality data in order to do simulations. One way would be DER management, and we have reactive power management. We have load management in place, and we have ICT-based technologies, control technologies for the distribution grid. What I'm going to focus more on is like the DER management and the ICT part in this particular grid, because I have to admit that for planning time of German grid extension, reactive power management and load management is not of a big benefit. So, but that's for planning time of distribution grids. So, one big issue is actually if you cut the DER peak feed in. That's some kind of envision we had by the local German utility in Oldenburg, the EWE. They said we have this 5% approach we do. We cut the upmost 5% of the DER load, and we found out that we save a lot of grid extension on that one. And we calculated that for the individual scenarios. So you see, we took all those scenarios into account for both wind power plants and PV power plants. And the interesting stuff is that if you cut, and we just said, okay, that's 3% for us. If you cut like 3% of the DER peaks, which is actually not a lot, because how many times do those peaks occur? And you plan your grid for those peaks. If you may cut them, you may change your total planning, and that reduces up to 50% of the overall grid extension. And remember those thousands of kilometers on individual voltage levels we have. So that's just one tiny step which saves a lot of grid extension. Not necessarily money, because you have to deal with the energy management and the control of the DER to cut their generation. But anyway, that's what I'm going to deep into in the further slides. So DER management in general in Germany cuts 50% of the grid extension and up to 15% of all costs. So that's an average cost saving till 2032 we have on this very figure of the maximum feed-in. We have to reimburse people for energy not being fed in, so that's the energy substitution we have here. And of course, we have to take into account the ICT costs for the individual communication lines, fallback solutions for 61850 based boxes to control DER and so on. But even if you calculate this into, you see that there's somehow like here you get an optimum. Right here somewhere it must be between 80 and 70%. So we were always a bit conservative and said, okay, we might save up to 15%. All the figures we have in the study are always the highest cost involved. So it's the worst case in terms of benefits you have. It will definitely be better if some things change in terms of, for example, ICT. The next step we took into it's in German, it's regelbare Ortsnetztrafo, so it roughly translates into intelligent voltage transformers. So in the low voltage grid, we had always the voltage band regulations on our simulations, and of course, intelligent voltage transformers can help there. Of course, it rises the additional cost for the ICT and the tap changer part of the conventional transformer up to 10%. But since we can also optimize the distribution of the intelligent voltage transformers in the German grid, we roughly need about 46,000 of all those aforementioned. In the fourth slide, I had the overall figures for the voltage transformers. Until 2020, we need like 30,000 new pieces. Of course, those voltage transformers might travel. because somehow a voltage transformer only helps up to a certain point, and then you have to do conventional grid extensions. So they are not always on the same place, but we have those figures in place. And it works pretty much in every scenario. And of course, we have less investments in terms of cable being digged into the ground or put onto landlines. We have less investments on voltage transformers because we also save conventional transformers, but we have to pay for the intelligent voltage transformers and for the ICT part. So, combining measures, actually if there's one great thing and another great thing, it doesn't usually combine. So I like chocolate and I like fish, but it doesn't really combine as a meal. So we also had to look whether that works if we combine the intelligent voltage transformer and the energy management for the DER generation. But it does, actually. So it's not the same that they just add up, but if we have conventional extension, we have up to 1.3 million euro per year as additional costs. Then we have, like, with generation management, as I mentioned earlier, we have like a 50% cut, and if we combine it with all the individual costs for intelligent voltage transformer, we have an additional 5% and might save 20% annual costs on the grid extension needed. So, basically, summary, conventional grid extension is really costly. So we have a lot of money to be put and buried into the ground till 2032. The scenarios may actually differ, but we have between 130,000 and 280,000 kilometers of more lines in general. The grid fees for the customer might rise up to 20%. That's not acceptable by the government in terms of being politely to the people actually voting for them. So it's also not equally distributed. You have the problem in the eastern part of Germany and a lot of problems in the southern part of Germany. So the spread between the grid fees is rising, and we try to put the scissors back together. Also, 70% of all extensions are in the first 10 years till 2032. So that's, in short terms, we have to build in for maximum DER penetration of the German distribution grid. And the conventional extension also has, like, it's always a scenario for all DSOs in general, but some are involved, well, that's fine, but those are really heavily involved. You can pretty much put them out of business when you say, oh, we do it this way, under those regulation regime. So 1/3 of all low voltage and 2/3 of the medium voltage grid operators are involved, and up to 70% of all medium voltage are penetrated by, actually, or impacted more or less by the DER extensions and by the grid extensions following in the next 20 years. We have a different regional density, so 60% of all LV extensions are in the south of Germany due to the PV feed-in, and the HV extensions are mainly in the north and in the eastern part of Germany. And of course, regional technologies drive this in terms of the DXR extension. So it's easier to actually cope with the SCADA system and the generation management of a large offshore wind power plant than with 25,000 individual PV panels in Bavaria in Germany. So what we actually did and what we took into account in terms of changing the way of how to plan for the distribution grid. Yeah, I didn't see that coming, so you could have assassinated me anyway. That's a little frightening. So actually, we have, like, a reduction of the grid extension by like 60% in terms of the overall extension, which doesn't mean cost, but at least less stuff to bury. We have a cut optimum for Germany, not necessarily for the individual DSO, I have to admit, of 3%, which leads to a reduction of the grid extensions by like 40%. The intelligent voltage transformer can provide an additional 20%, and then we run up to 60% in not building new lines or cables in the distribution grid. That only means a cost cut by like 20%, but anyway, it's money, because the ICT part leads to higher operational expansion costs and capital expansion costs of around those 10,000 intelligent voltage transformer we definitely need. So the 46 I had in the earlier slides were like if we only do voltage transformers, but no DER generation management. The Of course, one problem is that under the regulation regime in Germany, they always differentiate between CAPEX and OPEX. And the problem is that the OPEX costs, so the operational costs annually, rise from around 16% to up to 40%. And that should be somehow brought into account by the regulator, because that is something the utilities are really keen on, having it clear that they just don't put something and then they say, okay, next year we get the money back, but that they got annual reimbursement for the individual parts. So we have like the 3% cut of the DER generation feed in. It's quite easy in terms of the concept, I have to admit. I mean, there are still some technical challenges. Because you always cut the peaks and reimburse people for the non-fed-in peaks. So there's even all the replacement energy taken into account. So people don't lose money, but you do not have to plan your grid for the peak. Of course, with the energy management system, so just to bring up, who did direct control of DER systems over wide area networks in this room? Just raise your hands. If nobody raises their hands, I have some time, so I can talk about that. It's pretty difficult, because you have to talk to a device which is probably in an area where you have no mobile grid, where you have a bad digital subscriber line, DSL around, where you have barely GPRS, not even LTE or whatever. So you can never be sure whether, if you want to shut down the DER, it actually works. So you have to work with heuristics there anyway, or make sure that you have a pretty decent ICT in place, and pretty decent ICT is, of course, with the integration into your SCADA system, always a bit more tricky. In Germany, we have an additional problem, which I didn't mention at all, and this we have the so-called smart meter gateway. It's called the Intelligent Measurement System, the Intelligentes Messsystem, the IMSIS in Germany, and they want to channel every communication to controllable local systems, even DER, through this meter gateway, which is of course more costly in terms of ICT, because you have also the complexity of integration in an individual household, whereas you could also go like bypass the metering gateway and control directly the DER through a SCADA system. So this is still subject to discussions in Germany, which technical architecture will be the way to go. Luckily for us, it's the same price. So the distribution of the individual parts and the cost is different, but it adds up to pretty much the same overall sum. The regional costs gap in Germany closed using our intelligent technologies. So the grid fee, the high rise of the grid fee was lowered for the North and East German customers, and a bit raised, we don't say raised, for the southern Germans, because no one wants to pay more grid fee to lower the gap between. But anyway, this is how it works if you have like one country. So that was basically the story, so I'm open to questions. And normally I could talk for hours on this issue, because it was really fun to do this study in the team, because we are from so different disciplines, and first up front we had to agree that we wanted to trust each other and use the same words. But it's really well worth reading. For this event, I could somehow trick our Ministry of Economics into financing a translation of the complete management summary of the study. So unfortunately, all the 250 pages are in German, but I will send Henrik a PDF of 25 pages translated into English with the core results of the study for you to read. Thanks.
Thank you very much, Mathias. A very interesting presentation about the German DERs, and it's never easy to be the first speaker in the morning, but I think you got the audience attention, so there'll probably be some